Yellowstone is dangerous, but something deeper may be stirring across the west. Strange Utah holes and thousands of hidden quakes hint that the region is far more active than anyone realized.
Following up after a small eruption at Yellowstone National Park took visitors and experts by surprise, but scientists say it's just the latest in a series of blasts they're tracking after a much larger explosion last summer.
It's almost a dare, whispered in the cracks of America's bedrock. If you think Yellowstone is the worst nature can do, think again. Beneath the forests and geysers, Yellowstone hides one of Earth's largest ticking bombs, a supervolcano with the potential to devastate much of North America. The documentaries get it part right. Yellowstone could destroy America. But we're distracted by Wyoming's boiling springs, while the deep Earth may be setting a stage for something far bigger. The signs are rising through seismic screens. New supervolcano activity, unexplained holes tearing through Utah's desert, the discovery, by AI, of nearly 86,000 earthquakes that slip through unnoticed, a swarm of shakes big enough to rewrite how we see the ground beneath our feet. To grasp the real risk, you have to peer through the smoke and geyser steam and see the planet as geologists do. Yellowstone is a monster, but just a part of a vast system of supervolcanoes and tectonic powers that have changed civilizations before and may do so again. And the next disaster isn't just a possibility, it's a matter of time in geological terms. If Yellowstone sleeps, what else waits, maybe even angrier, below? Is there something far more devastating under our feet, waiting to awaken when we least expect it? Grab hold, because today we're diving into the world's deadliest geology, the truth about earth-shattering earthquakes, and the real ticking clock that overshadows even Yellowstone. Are you sure you want to know what's hiding below? Chapter 1. The Yellowstone Supervolcano Threat. Picture a force so immense it could alter the climate of an entire hemisphere in hours. Yellowstone isn't just geysers and hiking trails. It's an ancient caldera, pulsing with molten fury. Yellowstone's supervolcano has the power to unleash ash clouds that circle the globe, darkening skies and threatening life as we know it. While the notion of instant destruction is dramatized, the underlying threat is very real. A major eruption at Yellowstone could have severe consequences for agriculture, climate, and daily life. Why is Yellowstone's eruption seen as a civilization-ending event? And how close are we, really, to disaster? The heart of Yellowstone is a boiling chamber of magma spanning over 30 miles across. This isn't just hot rock. It's a pressurized reservoir with enough energy to alter the course of history. Signs of this power are everywhere. More geysers and hot springs than anywhere else on Earth. Superheated water reaching up to 192 degrees Fahrenheit. And a landscape that rises and falls as pressure waxes and wanes underground. When Yellowstone last erupted on a supervolcanic scale, it blanketed much of North America in ash and contributed to global climate disruptions. Scientists keep watch for warning signs: earthquakes, ground swelling, changes in gases, and shifts in surface temperature. While an eruption could be catastrophic, there is currently no evidence suggesting it is imminent. Still, Yellowstone remains one of the best monitored and most potentially dangerous volcanoes in the world. But if this isn't the only threat, what else lurks beneath the Earth's surface? Chapter 2. Supervolcanoes, the ultimate killers. Now imagine Yellowstone doesn't go first. What if there's something larger, orders of magnitude stronger, lurking out of sight? What actually qualifies a volcano as a supervolcano? And why are these events both rare and so deadly? Supervolcanoes are defined by eruptions that eject more than 1,000 cubic kilometers of volcanic material, thousands of times greater than typical eruptions. These events are rare on the timescale of human civilization, but their impacts are profound. Yellowstone is famous, but it's not alone. Other supervolcanic calderas exist: Toba in Indonesia, Taupo in New Zealand, Campi Flegrei near Naples, and more. Each is capable of injecting enormous amounts of ash and gases into the atmosphere, causing volcanic winter conditions, drops in global temperatures, failed harvests, disrupted weather patterns. Their footprints can span continents, leaving lasting scars on the landscape and on human history. Supervolcanoes don't erupt often. Many have intervals of hundreds of thousands of years, but when they do, the consequences echo for millennia. A single such eruption could stress world food supplies and modern economies beyond breaking. Could humanity, even today, withstand the fallout from another supervolcanic cataclysm? Chapter 3. Unseen Giants, the Hidden Supervolcanoes. Most people can point to Yellowstone on a map, but what about the ones that don't advertise their danger? Where do we find the world's hidden supervolcanoes? And how can something so colossal remain largely out of sight until it's too late? Many supervolcanoes are concealed beneath the surface, under deserts, seas, or even populated areas. Scientists have identified mysterious giant holes appearing across Utah's desert, signs of subsurface instabilities related to the region's complex geology. Other such features, like the Toba Caldera, appeared as ordinary lakes or plains until their true origin was revealed through careful geological mapping and satellite imaging. Some are only recognized as supervolcanoes after evidence of titanic ancient eruptions is unearthed. Miles-thick ash layers, massive depressions, or unusual patterns in seismic waves. Recent findings, like earthquake swarms and heat anomalies, help highlight which of these giants might be stirring beneath the world's quiet corners. Could the next super eruption come from a volcano humanity has barely begun to understand? Chapter 4. Yellowstone's explosive geology exposed. Steam billowing from the ground, acid pools bubbling, and a landscape in motion. Is this a tourist wonder or a warning sign? What makes Yellowstone's geology uniquely volatile? And what hints does it provide about the next one? Yellowstone sits atop a hotspot, a deep plume of hot mantle rock piercing Earth's crust. This setup has created a landscape unlike anywhere else in the world. Over 10,000 hydrothermal features, including more geysers and hot springs than anywhere else on the planet. Satellite data and ongoing measurements show that Yellowstone's ground rises and falls in response to changes in the underground magma chamber's pressure. The surface caldera is just the visible scar of larger magma systems that reach deep into the Earth. These hidden chambers can inflate and deflate, producing subtle stress changes and the potential for future eruptions. The extreme geothermal activity is both a bellwether of geological unrest and a template for monitoring other supervolcanoes around the world, where similar surface clues could offer precious warnings. With all this activity, can we ever truly predict what comes next? Chapter 5. The Shockwave, Eruption Consequences. Plumes of ash, sunlight blocked, sudden global winter. What would really happen if Yellowstone or another supervolcano exploded? Just how far-reaching are the effects of a supervolcano eruption? And could humanity withstand the aftermath? The physics are as chilling as the consequences. A supervolcano's eruption would loft enormous quantities of ash and sulfur gases high into the atmosphere, forming a global sunshade. This would cool the Earth's surface, disrupt climate systems, and drastically reduce crop yields, a phenomenon known as volcanic winter. The Toba eruption about 74,000 years ago is believed to have triggered such a winter, lowering global temperatures and causing severe environmental stresses. Even with modern technology, a super eruption could ground flights worldwide, damage power and communication networks, jeopardize water supplies, and lead to food shortages. While millions could be affected immediately, the longer-term risk to civilization comes from years of climate disturbance, resource scarcity, and social upheaval. Survival would depend as much on preparation as on luck, but the challenge would likely test the resilience of every nation affected. Chapter 6. Earthquake swarms. A hidden alarm. A single shake grabs headlines, but what about tens of thousands? Quiet, subtle, almost invisible. How did AI change our understanding of seismic risk? And what do the discovered earthquake swarms really mean? A recent leap in seismic analysis, powered by artificial intelligence, has revealed that the Yellowstone region experienced nearly 86,000 earthquakes over a recent 15-year period. This is a strikingly higher number than formerly estimated, showing that what was once thought of as background noise is actually an intricate, dynamic web of seismicity. Most of these tremors are too small to be felt, but clusters, known as earthquake swarms, can indicate magma or hot fluids moving underground. Such swarms sometimes precede volcanic activity, acting as a stress signal from the deep earth. The discovery doesn't guarantee disaster, but it does mean scientists now have a much clearer view of underground processes and a better chance to spot potential signs of bigger threats. If Yellowstone is shaking this much, what about other, less monitored calderas around the world?
Chapter 7.
Geysers and hot springs, portals to hell. Beneath the postcard beauty of geysers, where water hisses and dances in superheated jets, there's a crack to Earth's furious core. Why do geysers and boiling springs cluster atop supervolcanoes? And what secrets do they reveal about coming eruptions? Yellowstone contains the world's highest concentration of geysers and hot springs. These features form as rainwater and snowmelt seep underground, get heated by hot rock or magma, and return to the surface in explosive displays. Their appearance isn't just for show. Their activity signals the energy building beneath. When the patterns of eruptions or the temperature and chemistry of waters change, it can be a clue to shifts in the underlying magma system, sometimes a sign of threat, sometimes part of natural cycles. Scientists vigilantly monitor geyser activity and chemical emissions, hoping for early warnings, but the signals are complex and sometimes ambiguous. Even so, these hot springs and geysers grant us front-row seats to the drama deep below Yellowstone's crust, reminders of the forces at work.
Chapter 8.
The most dangerous caldera known. If Yellowstone frightens you, consider the Toba supervolcano, Indonesia's buried monster, whose ancient eruption may have threatened humanity's survival. What made the Toba eruption so deadly? And could a similar event repeat on today's populated planet? About 74,000 years ago, Mount Toba erupted with a force unmatched in the last 2 million years, ejecting over 2,800 cubic kilometers of material. The resulting ashfall covered large regions of South Asia and affected global climate, possibly triggering a volcanic winter that lasted several years. Some scientists speculate, based on genetic evidence, that the eruption contributed to a human population bottleneck, although this remains debated. The Toba caldera remains an enormous, water-filled scar, a constant reminder of what Earth's most powerful volcanoes can unleash. As global populations cluster around other caldera systems, the next super-eruption, whether in Indonesia, Yellowstone, or elsewhere, would have even more far-reaching social and environmental effects.
Chapter 9.
New discoveries. Giant desert holes. Utah's desert should be quiet and stable, yet mysterious gaping holes have appeared, startling, unexplained, and possibly linked to ancient supervolcanoes. What can giant holes in the desert bedrock actually tell us about risks below? Many of these holes, or sinkholes, are formed when water dissolves underground rock, or when the collapse of old lava tubes leaves the surface unstable. In volcanic regions, such collapses may reflect formerly active magma systems, or zones of buried geothermal energy changing over time. While not all sinkholes are connected to imminent volcanic risk, their occurrence highlights the dynamic nature of Earth's crust, where instability or ground collapse sometimes marks areas of ancient volcanic activity. Geologists investigate these features for clues to hidden hazards, aware that such events underline how little we may understand about the forces shaping our landscapes.
Chapter 10.
Supervolcano clusters, the domino effect. We think in terms of single threats, but geology does not respect such boundaries. Some regions host clusters of calderas, hinting at immense, interconnected zones of danger. Could a single eruption destabilize other supervolcanoes? And what does that mean for global survival? Geological studies indicate that supervolcanoes often occur in regions of thin crust, mantle plumes, or ancient tectonic weakness. Sometimes, multiple calderas form along such zones, effectively creating chains of volcanic infrastructure. While one eruption triggering others is not a proven scenario, The interconnected nature of magma systems raises the possibility that significant geologic events in one area could influence stresses nearby. The vastness and complexity of these systems mean monitoring is vital. Understanding how one explosion might affect adjacent calderas pushes the boundaries of volcanology and risk management. Could an eruption in one caldera start a sequence that affects a whole region? It's a question researchers are still exploring. Chapter 11. The AI Seismic Revolution. For centuries, humans have tried to read Earth's language, but only now, with AI, are we learning to listen. What game-changing discoveries has AI brought to earthquake and eruption forecasting? And do they make us safer or more aware of our vulnerability? By deploying artificial intelligence to seismic data, researchers at Yellowstone and elsewhere have uncovered tens of thousands more earthquakes than previously catalogued. Most of these are tiny, undetectable on the surface, but their patterns provide vital insights into the movement of fluids and magma. AI analyzes far larger datasets than humans alone could process, picking out swarms, anomalies, and elusive signals that may point to future unrest. This revolution in monitoring doesn't guarantee perfect prediction, but it sharpens our understanding and may eventually lead to better forecasting of volcanic events worldwide. Chapter 12. Yellowstone's Glacial Legacy. Underneath the churn of hot springs lies another force, scars left by ancient glaciers that reshaped valleys and forests. How did ancient glaciers influence the Yellowstone supervolcano's environment? And why does this matter for future eruptions? During the last ice age, glaciers up to a mile thick carved and molded the Yellowstone region. When the ice retreated, it left behind a patchwork of sediment and fractured rock, a terrain that more easily transmits groundwater and geothermal heat. This history influences how magma, heat, and water circulate today, making Yellowstone's eruptions and hydrothermal systems distinct from other hotspots. The weakened zones left by ancient glaciers also create pathways for magma and fluids to reach the surface. The glaciated past prepared the ground for today's dramatic geothermal displays, and perhaps for future geological unrest. Chapter 13. Chemical Warnings. The Smoking Gun. Nothing in nature happens without a trace, and in Yellowstone and beyond, scientists vigilantly monitor invisible chemical signals for evidence of brewing unrest. What chemical clues show a supervolcano is stirring, and can we trust them to give us time to act? Hot springs and fumaroles in Yellowstone continually emit gases, sulfur dioxide, carbon dioxide, hydrogen sulfide, and trace elements carried up from deep underground. Increases in these gases can result from new magma moving upward, heating groundwater, and releasing previously trapped volatile compounds. Monitoring enables researchers to detect spikes or unusual patterns that might signal imminent changes. While gas emissions are essential clues, their interpretation is complicated. Non-eruptive variations can mimic warning signs, making chemical surveillance a crucial but uncertain part of supervolcano prediction. Chapter 14. Catastrophic Feedback. Volcanic Winters. An eruption is not the end of the story. It provokes a domino effect across atmospheric and climate systems. Supervolcanoes don't just destroy near the source, they set the whole planet's thermostat. What is a volcanic winter, and why did it nearly erase humanity before? A supervolcano injects enough ash and sulfur compounds into the stratosphere to reflect sunlight, leading to dramatic cooling for years, sometimes decades. The volcanic winter after Toba's eruption may have accelerated global cooling, shrunk populations, and led to famine and environmental collapse in some regions. While the link to a human genetic bottleneck is still debated, the potential for similar disruption today is sobering. Volcanic winters threaten worldwide food production, water resources, and infrastructure. And because their onset can be sudden, modern society, with its interconnected systems and reliance on global trade, could be particularly vulnerable. Chapter 15. New supervolcano activity detected. Earth's deep plumbing remains mysterious, but modern technology is revealing more than ever before, sometimes to unsettling effect. How do scientists actually detect new supervolcano activity? And what could these findings mean for our future? Through a combination of deep drilling, satellite thermal imaging, seismic monitoring, and gas analysis, geologists now spot subtle anomalies that might signal the stirring of ancient calderas. Not only Yellowstone, but other supervolcanoes around the world have shown changes: magma signatures, rising heat, small earthquakes previously overlooked. While many such findings may relate to ongoing background processes, the improved resolution of our monitoring brings earlier and better warnings. As more calderas display hints of activity, scientists balance caution with curiosity. Are we witnessing normal geothermal cycles, or the first stirrings of future super eruptions? The question remains open and under constant review. Chapter 16. Sand Mysteries. The most sand on Earth. Beneath the ashen rock, Earth's crust hides another secret: vast deposits of sand, shaped by ancient volcanic violence and relentless erosion. Why do volcanic regions boast such abundance of sand? And what can this tell us about past cataclysms? Sand in volcanic areas often results from the gradual breakdown of lava, ash, pumice, and other volcanic materials, a process accelerated by glacial grinding and the passage of rivers. Each grain represents the aftermath of cycles of eruption, collapse, and renewal. In places like the Yellowstone region, these sands record layers of past violence, climate shifts, and landscape transformation. Geologists painstakingly sift through these deposits, compounding a record of mega eruptions and clues about the landscape's historic and future resilience to geological upheaval. Chapter 17. The Coming Reckoning. Here's the truth science can't ignore. The ground beneath us is not solid, but restless, a thin skin over a cauldron of fire and time. Yellowstone, with all its power, is but one face of a global threat. The real lesson is broader than any single eruption. Our planet is shaped by cycles of destruction and renewal, often beyond our capacity to control or predict. Earth is indifferent to our timetables, our borders, our civilizations. The warnings in documentaries are rooted in geological truth. Supervolcanoes have starved populations, reshaped climates, and altered the very path of life on Earth. They will do so again. The planet's deepest secrets surface not in myths, but in data: measured vibrations, chemical spikes, and slow-motion collapses in empty deserts. Our best hope is to monitor, study, and strive to understand, but ultimately, we remain at the mercy of a planet whose processes are older and greater than us, forces that slumber and awaken on timescales we scarcely comprehend. When the next great eruption comes, whether at Yellowstone or from a larger caldera on the far side of the world, civilization will face one of its oldest adversaries, a living, shifting planet that cares nothing for our plans. All we can do is watch, wonder, and hope we see enough warning to weather the storm. If you want to uncover more of the Earth's terrifying mysteries, subscribe and join us for the next deep dive. The greatest story our planet has to tell is still unfolding, and this is only the beginning.